So after doing all these kind of crazy examples, you're probably ready for a little bit of a break, or you're probably at least hoping we're almost done with this section. And the good news is, I think in this video, you're going to get something of a little break, and yes, we're almost done with this section. First thing I want to show you is what I call a tricky application of integration by parts. It's not nearly as hard or cumbersome as some of these examples we've done before, but it's one where you wouldn't think you'd use integration by parts, so I want to do it for you. It comes into play when you're taking the antiderivative of the natural log of x. We've talked about this a little bit. You might think you know the antiderivative of the natural log of x, but you don't, right? If you're thinking it's 1 over x, no, that's the derivative of natural log of x. We don't know the antiderivative of the natural log of x. But it turns out, kind of interestingly, that you can figure out this antiderivative by using integration by parts. You're like, how does that work? It's the natural log of x. It's not the natural log of x times something. I thought you could only use integration by parts when it was something times something. And you're kind of right. I mean, the idea with the integration by parts formula is it's the integral of u times dv that's equal to u times v minus the integral of v du. But what I'm going to do over here when I choose my values of u and dv is almost cheat. For u, I'm going to choose natural log of x. And you're like, okay, sure. I mean, that's the only thing you could choose. But then what's dv? Well, if natural log of x is gone, all that's left is kind of an implied 1 here. 1 times dx. I could think about the natural log of x dx as the natural log of x times 1 dx. Because you can always multiply by 1. And you're like, all right, that kind of feels like it's not going to get any simpler. But actually it is. Because look what happens with these choices. If u is the natural log of x, then du is equal to 1 over x dx. And if dv is equal to 1, then v is equal to x, right? Because the derivative of x is just 1, so the antiderivative of 1 is equal to x. I have these 4 pieces. I can use them in this formula. The integral of u, natural log of x, times dv, 1 dx, is equal to u times v, so x natural log of x, minus the integral of v du, so x times 1 over x dx. By doing this kind of clever application of the integration by parts, I'm left with an integrand that doesn't involve the natural log anymore, which is kind of cool, right? Because I didn't know how to take the antiderivative of natural log, but I never needed to because I used that up in the u. So it allowed me to get around ever figuring out the integral of the natural log of x. All we have to do is figure out the integral of x times 1 over x. And good news on that, x times 1 over x simplifies really nicely. X times 1 over x is just equal to 1. So it's the integral of 1 dx, which is something that we can figure out. In fact, it's something that we've already figured out. It's just equal to x. So this simplifies to x natural log of x minus x plus c, which I think is kind of cool. The antiderivative of natural log of x dx is x natural log of x minus x plus c. Who knew? And whoever would have thought to use integration by parts to come up with it? In case you think that this was some like smoke and mirrors thing and this doesn't work out, look what happens when you check your answer. When you take the derivative of x natural log of x minus x plus c. Let's think about what happens. Going back to chapter 2, we got the derivative of a sum or difference of 3 different terms. So we take the derivative of each one individually. X natural log of x minus the derivative of x plus the derivative of a constant. For the derivative of x natural log of x, I'd have to use the product rule. So I take the derivative of the first thing, the derivative of x, which is just 1, and then I'd multiply that by the second thing, the natural log of x, and then to that I would add the derivative of the second thing, which is 1 over x, times the first thing, which is this x. The derivative of x natural log of x produces this stuff, using the product rule. But I'm not done. I still have to take the derivative of x. The derivative of x is just 1, so I got a minus 1 here. And then the derivative of a constant is just 0. I don't have any derivative symbols here, so I'm kind of done, although I can clean this up a little bit. 1 times the natural log of x is just the natural log of x. 1 over x times x is just 1, so I have plus 1, minus 1, plus 0. Wait, plus 1, minus 1, plus 0, isn't that all just going away? Yup. So your derivative is just the natural log of x. Oh, neat, that simplified really nicely. What were we doing again? We were proving that this was the antiderivative of the natural log of x. And we just proved it, right? Because we took the derivative of this thing and we reproduced the x. The antiderivative of natural log of x must be what you see in blue because the derivative of what you see in blue is exactly the natural log of x. It's not that hard. It's not as hard as the examples we've done before. It's just tricky because unless I had shown you, you probably wouldn't have thought to use integration by parts when we don't really have a product here in the integrand. That's one of the two leftover things that I wanted to show you. The second of the two leftover things is not related to that at all. Well, that's a bit of a lie. It's coincidentally related to what I just showed you, but really it's meant to serve a different purpose. What I want to show you is, what about definite integrals? Everything we've done in this section has dealt with indefinite integrals, but what about definite integrals with the integration by parts formula? Well, the way I like to think about it is, anytime you're doing a definite integral, what you're doing is you're figuring out the antiderivative, in other words, doing an indefinite integral, and then at the very end you evaluate it. So if somebody asked you a question like the definite integral from 1 to e of the natural log of x squared, what you could do is answer a different question. You could figure out the integral of the natural log of x squared dx, figure out this answer, get this answer, and then evaluate that from 1 to e. So that's what we're going to end up doing. What's the integral of the natural log of x squared dx? Well, it's not easy, but what we could do is think about this as the integral of the natural log of x times the natural log of x dx. Something times something, oh, I wonder if it makes sense to use integration by parts. Let's try it out. Let's let u be equal to the natural log of x, in which case dv is this other natural log of x dx. I'd need to figure out the derivative of u, but du is just 1 over x, the derivative of natural log of x. And then I'd have to figure out v. And that's a little bit challenging because generally the antiderivative of natural log of x is really hard to figure out. But fortunately for us, we just did that up here. Just a minute ago, we figured out that the integral of the natural log of x is x natural log of x minus x plus c. So what I can write right here in v is x natural log of x minus x. I don't have to write the plus c. I now have my 4 pieces, so I can use my integration by parts formula. My integration by parts formula tells me that the integral of u dv is equal to u times v, so natural log of x times x natural log of x minus x, minus the integral of v du, so 1 over x times x natural log of x minus x dx, which I forgot to write right here. Whoa, this looks a lot harder than the original question. Kind of. I think this is uglier than the original question, but I think this will be easier to evaluate the antiderivative of. Over here, let's just leave stuff alone. The natural log of x times x natural log of x minus x, all in parentheses. And let's work over on this integral. I got 1 over x times this thing, so I can distribute the 1 over x to each term. If I distribute the 1 over x to the first term, I'm left with just the natural log of x. If I distribute the 1 over x to the next term, I'm left with a negative 1. So what I have to take the integral of is the natural log of x minus 1 dx. Good news, we can take the integral of the natural log of x minus 1 dx, because when we have sums and differences, we just take the antiderivative of each term individually. So I leave all this stuff completely alone, and then I'll subtract this integral. What is this integral? Well, the antiderivative of natural log of x, fortunately, is something that we figured out up here. I'm really taking advantage of that. It's this x natural log of x minus x plus c. I don't have to write the plus c. So this antiderivative goes here, and the antiderivative of negative 1 is just minus x. The antiderivative of natural log of x minus 1 is x natural log of x minus x minus x. I tack on the plus c, and I'm done. As you know, I can't help myself and I have to simplify these things. I take this natural log of x and distribute it into these parentheses to get x times the natural log of x squared minus x times the natural log of x. And then from that I want to subtract this x natural log of x. And then this negative x and this negative x I can call minus 2x. So I'm subtracting minus 2x. I got plus 2x plus c. You could easily call this good enough. Although I think I want to take it one step further. I just want to recognize that I got an x natural log of x here and an x natural log of x here. And since they're both negative, I really have minus 2 x natural log of x. There's other ways you could write your final answer, but I think I'm going to be content with writing it as x natural log of x squared minus 2 of these x natural log of x things plus 2x plus c. Kind of a crazy antiderivative to figure out. You're like, wow, at least we're done. Well, not really. What we answered was this question. Remember, the whole purpose of this extra part here was to talk about definite integrals. The question we were supposed to answer was this definite integral. But the good news about this definite integral is it's just the indefinite integral evaluated from 1 to e. So all I got to do is copy this answer, x times the natural log of x squared minus 2x natural log of x plus 2x. I don't have to write the plus c because I'm going to evaluate this thing from 1 to e. Evaluating this from 1 to e just means plug in e's everywhere you see an x. So I got e times the natural log of e squared minus 2e times the natural log of e plus 2e. And then from that huge mess, I want to subtract what I get when I change all the x's into 1's. So 1 times the natural log of 1 squared minus 2 times 1 times the natural log of 1 plus 2 times 1. Fortunately, because I chose 1's and e's, this is going to simplify really nicely. The natural log of e is just equal to 1, and the natural log of 1 is equal to 0. Some log facts that you may have known at some point in a pre-calculus class. So this natural log of e is just a 1, and 1 squared is just 1. So I got e times 1, or just e, minus 2e times the natural log of e. But again, this natural log of e is just equal to 1. So it's minus 2e times 1. In other words, minus 2e. And then I have this plus 2e. And then from that whole mess, I want to subtract. Well, the natural log of 1 is just equal to 0. So 0 squared is 0. 1 times 0 is 0. So I get 0 here. Minus 2 times 1 times another 0. So subtract another 0 plus 2. This negative 2e and this positive 2e cancel out. And this whole parenthesis just simplifies to an e. Over in this whole parenthesis, it simplifies to just a 2. So I get e minus 2 as my final answer. That kind of simplifies really nicely. But the point is less about the simplification and more to show you that when you have definite integrals, what you can do is just evaluate the indefinite integral and then take that answer and evaluate it according to the endpoints that you're given. That's all I got on integration by parts, so let's call this section good.